the straight line. So A to B straight line is the result of an optimization process. The Euclidean distance is itself the solution of an optimization process. And I've got my white dot here. I can move from A to B along that path. And in doing so, I'm transforming what was at A to something that's at B. Yeah? If my white dot moves linear along that linear path, in fact, on any path, it's a form of a transformation from A to B. So there's the two concepts, just by measuring distance. Distance is itself a concept which is the result of an optimization process, and a transformation is also defined. So distance and transformation, and they're the two elements in the subject of optimal transport. A misfit function between two objects, like some sort of data that you might observe and some sort of predictions from a model, might be described as what it can be described as a distance function. It's the distance between the two objects. So I think we can all agree on that. And a misfit function corresponds to it also to a transformation between predicted and observed. And that's a slightly unusual way of looking at things from an inversion perspective, but we are asking, there's always a transformation between A and B when we define a misfit function. And it's the path in this case that the white dot goes between A and B. So distance and transformation are wrapped together in terms of how far away one thing is from another. Now, before I go into what optimal transport is, I'm going to give you an example, just give you some nice movies and some pictures to get a feel for what it is before we go into a bit more of a formal discussion about it. So on the top there, now I can just about now, can you see my, I've lost my let's just go here, my spotlight. I hope you can see my spotlight. Yes, I'll assume you can. Nope, it's gone again. I'll get it back, excuse me. Okay, spotlight. I hope you can see my red dot. On the top, I start with two simple Gaussian functions in blue here. And I'm going to describe them as the starting point. They might be my predictions from my model. And let's say the dashed line is my endpoint, my red dot. It is the data that I want to fit. Okay. Now I'm going to animate the least squares path between the green to the red dot in the top figure, and we'll see how we move in a Euclidean distance between the two Gaussians and the one Gaussian. We must end up at the red dot, so we will end up at the single Gaussian in the middle, but we're going to look at the pathway. Now, you can guess, have a little guess to yourself what the shape of this animation might look like before I play it. I'll give you 1 second to pause. How is the blue going to hit the dash line? And we'll play it here. And I don't know if you can see the animation because I can't. Can you see the animation? Let me get rid of my dot and try that now. Can you see the animation? Because I can't see it happening.
No, it's not showing.
It's not showing. Bugger. Okay, so what you would see, let me try and do this again. I'm going to unzip that and just try and play it there. Can we see it? Oh, bugger, you can't see it. Okay, what you would see, unfortunately, and you don't, are the two Gaussians decreasing in amplitude and the one in the middle increasing amplitude from 0. Yeah. Essentially, Euclidean norm just moves the amplitude at a fixed, and let's call it time here. So the two blues will go down and a white and the middle one will appear. Optimal transport does something quite different. And we may actually, you won't see that animation either, I guess. Let's try that. No, unfortunately, it's not working. Okay. The blue will move both horizontally and vertically. So the blue, the optimal transport path between the two, actually joins the two Gaussians together. They will flow, the left one will move to the right one will move to the left, and they'll merge and increase in amplitude. That's the effect. And the starting point and the end point are the same, but the path is different. And that's given on the left-hand side here that the two endpoints are the same, but a path is different. And because the path is different, the distance will be different. So as you transform one object into another, you define different ways of measuring the distance between them. And we're going to use that as a Misfit function for an inversion. Now, I'll just have a quick go to see if we can't get that. What a bugger, unfortunately. This happened in training. It didn't happen on the night. Okay. So I'll jump over that then and show you a different form, a different example of optimal transport, which is a still image. Now, this is from the work of Solomon, transforming objects. And it's important, this idea of transformation. They're pretty and they're fun pictures to look at. The top one is a cow, a red cow, moving into a green duck to a blue torus. So we're changing the color and the shape. This is a particular form of optimal transport in a beautiful paper by Justin Solomon, I think, 2015, how one can map smoothly one object into another. And at the bottom here, we see it over a 2D plane. The cow is in the bottom left, the duck in the bottom top right, the right-hand side, and the torus is now green. We're unfortunately to swap the colors around. And you can see that anywhere across this plane, you can see the motion of transporting one shape into another. Now, why do we care? Well, it's a different, what I really wanted to get across in these pictures here is it's a different way of measuring distance, because as you transform, you go along a different path, and therefore there's a different measure of distance. And it's that character which determines the behavior of the distance function. And it will turn out that that will change the nature of an optimization-based inverse problem. Now, okay, so unfortunately we didn't see the videos, but I will distribute this to Alan and we'll put it the keynote up, and hopefully you'll see the videos yourself. You can play them later. Now let's just go back and go into some detail. I've always wanted to start a talk saying this story begins with Napoleon. And in fact, this story does begin with Napoleon. The modern subject of optimal transport traces its roots back to the tale of Napoleon and his mathematician, Gaspard Monge, a brilliant French mathematician who in the late 18th century, early 19th century, was asked by Napoleon essentially to shift, what's the optimal way to shift a load of sand. And here is a sort of an idealization of that problem. You can see, hopefully, I'll get my map. I've lost my pointers. Oh, so there we go. Well, I'll talk it through. On the left-hand side, you can see some orange piles of sand. They're disconnected. There's sort of 3 piles of sand there. And on the right-hand side, you can see 2 irregularly shaped holes that have been dug in the ground. Now, the total mass of the sand is equal to the total volume of the holes. This is a 2D case. And the question is, how do you transport the sand into the holes in the most efficient manner? Now, we define the answer to that as a mapping. We'll call it T of X here. I move the parcel of sand at X to the position Y. And I can always define such a mapping. Every part of X goes to a part of Y. And the question is, what is efficient? How do I define efficiency? And the work required, if you look at the physics of this problem, it turns out energy is proportional to distance squared times mass. So the mass is the volume of sand, and the distance squared could just be the Euclidean distance, the straightforward distance between X and Y. Simple X minus Y all squared. So the Euclidean distance could be our distance. So that suggests then that you could find the mapping which gives you the least energy, and that in a sense is optimal. But more generally, we don't have to stick with distance squared. We could equally define a problem here that didn't have distance squared, that had distance. And the expression I've got here of W2 squared is the one posed by Gaspard Monge, where C is my function of distance. It moves X to T of X, okay? And F of X is the amount of sand on the left. So if I integrate C times F over x, that is actually the sum of the squares of the distances times the mass. As I say, my distance function could actually be more general. It could be almost anything here. Now, this was posed by Gaspard Monge back in the early 19th century, and it wasn't clear that this problem even had a solution. We're trying to find t of x that minimizes w. And the w will stand for the name Wasserstein. This is the squared Wasserstein distance between the distribution f of x and the holes at g of x, the sand into the holes. Now, this problem was posed, but it wasn't clear there was ever a solution to it because it's nonlinear. A c of x there is actually quite complicated, and it isn't obvious that there will be a solution to the problem. Now, it wasn't until Kantorovich in 1942 essentially posed the same problem, but in a different context. And the modern field of optimal transport really starts with Kantorovich. He ended up winning the Nobel Prize for Economics in the mid-70s, and we'll see why in a moment. And Villani in the early 2000s wrote 2 books on this stuff. He's a mathematician, and really the mathematical field exploded in this topic from the work of Villani, I think it's fair to say. Okay, so we'll go through in a moment how these developments worked, but I want to now connect this concept to to geophysical inversion. Who looked at this idea and noticed that in Bayes, which is the top here, Bayes' rule, the posterior is a constant times the likelihood times the prior. Most people will understand that, and that's depicted on the right-hand side here by my figure, which is I've got a prior PDF, I've got a posterior PDF, and interpreting that geometrically, what does Bayes' rule actually tell us? It says that the amplitude of the prior PDF here, given by green, gets multiplied by the likelihood and becomes the amplitude of the posterior PDF, which is the red dot. Yeah. So the dashed line is my posterior, the solid line is my prior. So what Bayes' rule, it tells us only up to a multiplicated constant, k, because we often don't know k, almost always we don't know k. It tells us how the posterior relates to the prior at a particular point, M, a model for a particular model. Moving down to the lower part of the page, optimal transport provides what we call a push-forward deterministic map between continuous probability distributions. That's the mathematical framework here. One PDF is our pile of sand, the other PDF is our holes of sand. But really, we can think of mapping one probability distribution onto another. Now, in the context of Bayesian inference, what that means is, and I'm just trying to get over the geometrical concept here to compare it to Bayes' rule, is that we have a transport map. If we can find the transport map for an inverse problem, it means that P of M, the prior, at the model M, given here by the green line in the lower figure, exactly the same figure, gets moved. The model M gets moved to T of M, and it tells us where the posterior volume under a small element is equal to the prior. So you see the difference. The likelihood function in Bayes' rule tells us what happens at a particular M, whereas the optimal transport framework tells us where you move M to find the posterior that has essentially the same probability under an incremental element. So, and something immediately follows from this. What immediate follows is that the entire solution to every inverse problem is encoded in the transport map. I'll say that again. The entire problem for any inverse problem is encoded in the transport map, because the transport map takes the prior, it changes the location, it finds where we go to and gives you the posterior. Essentially, it's not quite at the same amplitude because it's the same volume in an incremental element. So the posterior is completely defined by the transport map, and therefore completely embodies the solution of an inverse problem in a Bayesian sense. And L. Moseley posed the idea, well, can we generate posteriors not by sampling, but by transforming the prior directly using the map? And that, I think, is a fascinating area. It shows you a direct connection between transport maps and the solution to inverse problems. Now, I'm not going to pursue that today because I don't know how to pursue it. I think it's a fascinating area. It's not obvious that this has direct practical implications, not yet, although, the work of L. Moseley has actually attempted to do this. There are certain technical issues about trying to recast inverse problems as the solution of an optimal transport map. But I think that's an interesting area, but it shows the connection, and that's my point here. Okay, to finish that off, what would be the implications if we had the transport map? We would have the prior, as shown in the middle here. We would transform every point on the prior to make the posterior. Well, let's compare that to Markov chain Monte Carlo. Typically, in Markov chain Monte Carlo, Bayesian sampling, we might generate samples according to a prior. And what the transport map tells us, well, we just take those samples and move them to a new point in parameter space, and they are then samples of the posterior by definition. Well, that immediately means we don't need Markov chain Monte Carlo anymore, because we simply generate samples according to the prior, we apply the map, and we have samples according to the posterior. We don't need all those wasteful samples in between. It's one in and one out. So by definition, we have a sampling algorithm which is perfectly efficient if we have the transport map. Now, the figure below is adapted from Solomon, again, 2015, but it's the work of Kantorovich, who showed that the transport map that I'm talking about is on the left-hand side. If we put our prior or any probability distribution on the top and the posterior on the left, one can think of this problem as finding the distribution in the box where the marginal is the prior at the top and the marginal on the left is the posterior. So this is the formulation of Kantorovich, and he showed that in doing this, you can actually solve these problems with linear programming, which means there's always a solution. It's well known, well understood, and can be solved. It doesn't mean it can be solved practically, but it can be solved in principle. On the right-hand side, the probabilistic transport plan, not map, plan, is a generalization of a map, and it exists when the problem is discrete, essentially. So in a discrete problem, the one-to-one mapping of the map becomes a probabilistic mapping in the plan. So that would mean you find the red dashed line here on the prior, and rather than it giving you a point on the posterior, it gives you a probability distribution there given by the cut that generates positions in the prior, in the posterior. So you can use the same idea. A plan is a higher dimensional beast, but it really only applies to discrete problems. So there's always a map in principle for continuous problems. Okay, so I just wanted to do that to show that optimal transport has a deep connection to inverse problems. In fact, it is directly the solution of an inverse problem in a Bayesian framework. So as I mentioned, the linear programming formulation of Kantorovich in 1942 was to discretize all of this. And it turns out that the W that I mentioned before becomes a linear sum of the distances between the points in one space, i.e. in this case, I'm generalizing it now, I'm not talking about Bayesian, a source probability distribution called F and a target called G. So Cij is the distance between 2 points, which are weights. Now we choose that in the sand problem, I just said Euclidean distance. So Cij is known in advance, you can always calculate it. And the idea is to find the Wasserstein measure, to find the transport plan, which I've written as pi ij here, that minimizes WP. And that's linear programming, which is well understood, was very popular in the second half of the 20th century. And there are many inefficient algorithms and some efficient ones to try and solve that problem. But it puts it in a context where we know there's a solution, and in principle we can solve it, And it turns out that there are other more inventive ways of trying to solve this problem. But now it becomes one of linear programming. So it's much more familiar, much more, the nonlinearity has disappeared by the fact that it's been discretized, and we look for a plan. Okay, so that was the work of Kantorovich, and that's actually really trivial maths to solve. Everyone can solve a linear programming problem, not necessarily quickly, but you can solve one. Hooray, hooray, it turns out that in one dimension, i.e. if you've got a if you've got a transport problem in one dimension, Villani showed that there is an analytical solution to that, i.e. And it's given by the integral I've got here. So we don't have to worry about the details of that, but it just simply says that it's an integral of two things that we can calculate. Now, if you take the, so there's no optimization required now, we've got bang or an analytical solution, but only in 1D when our probability distributions are in 1D. But many of our data sets are 1D curves. So on the top right-hand side here, if you take the starting distribution, which I've now swapped around, sorry about that, I'm calling the starting F and the, sorry, I'm talking, yeah, no, I haven't swapped it around. F goes to G. If you describe that as just a sum of delta functions, which really means you're just discretizing the probability distribution. So Fi are our weights now, and we target distribution G. Any two distributions, in fact, in principle, this works in any dimension, but in 1D, there's a particular advantage because if we take that discretization, put it into a Villani solution, you get the thing in the red box. And the red box is that the Wasserstein distance, i.e. the distance between two objects in an optimal transport sense, is just the product of two vectors, both of which are straightforward to calculate. I won't go into the details of what they are, but it's just delta Z times delta Y, the dot product of two things. So in 1D, we have incredibly efficient, fast, convenient solutions to this problem. I've introduced the variable P, that's just the power of the distance. I said you could have distance squared or distance to the power of 1, but any P you choose, typically P is either 2 or 1, you can calculate an analytical solution in 1D. And the figures below show my little implementation of this. So that's the linear programming as the size of the input, length of PDF. So as problems get bigger, linear programming scales very poorly, sort of often close to n squared, if not n cubed, but the computational cost goes up. But the analytical solution, of course, is relatively simple. It goes something like n log n. And on the right-hand side there, the green and the blue figures shows a much reduced scale. You see there's a 10 to the minus 4 factor, the computational cost of using an analytical solution compared to an alternative solver for this called the Monge-Ampere solver, which is another way of solving optimal transport problems for some cases. And you can see that they're comparable. The green beats the blue, as it would do, because the Monge-Ampere is actually a solution of a PDE, whereas the green is really just dot product in two vectors. You've got to calculate the two vectors, but once you've got them, you just dot product them. What's more in this is that this Wasserstein distance, which we're going to use as our Misfit function in inversion, it turns out with this analytical solution, we can differentiate it very easily. So we have exact solutions to derivatives, which is important if you're doing optimization. At least it's a big advantage if you're doing optimization. So there's the technical part of the talk over. We can do it in 1D very easily. In higher dimensions, it's more of a problem. Now, I just wanted to get on to an example of this. The rest of my talk can be about examples. I typically deal with seismic waveforms. Seismic waveforms inversion. Here I've got a receiver function example, and I suspect the movies won't work again. Nope, they don't work. So the bottom right here is a Misfit function as a function of two layered Earth models. So a layered Earth model here, a simple green on the top left figure is a shear wave speed of the crust. We've calculated a receiver function, which is a sort of a data product that, a function of the data, which is sensitive to the near crustal structure. And it's very widely used in seismology. But if we compare the difference between a predicted and observed function here, which is the blue and the gray, this is entirely synthetic, so we know where the answer is. The true model is the white dashed line in my figure here, and you can see the Misfit function as I've varied essentially the thickness of 2 layers. The minimum Misfit is in the foreground, and we have all these mountains of highly multimodal inverse problem, but that's simply because the waveform have what we call cycle skipping. It turns out that if you vary the velocity structure, which is the bottom figure here, the situation is very smooth. Sorry, that's the top one. The top one shows the waveform Misfit only varying a velocity structure. Hope you can see that. And the bottom one is a cut through this surface here. So as we vary the layers, positions, the layer thicknesses, it's highly nonlinear. If we change the velocity within the layer, it's actually quite unimodal. But this is the same problem we want to solve for both variables. So this is just a typical example of a problem that is highly nonlinear because of the multi-modality of the data, fitting phases, and you'd see that much better, I'm afraid, if the movies were going. Okay, we'll just move on. Now, breaking that down, again, you probably won't see the movie. The top is an example of an observed and predicted receiver function. Yeah, so my predicted is the blue, the observed is the white, and I want to compare essentially a least squares misfit, which is the top, to an optimal transport misfit is the bottom. And it's a bit like the 2 Gaussians here. So if we transform and look at the Euclidean distance between these 2 receiver functions in the top one, and what you'll see is the blue amplitudes decreasing or increasing and linearly going to the black amplitudes will map as we move from one to the other, and the least squares misfit is just the distance we move. Yeah? So again, the amplitudes, and I'll try, nope, we don't see it. In fact, we might see it. We see it better on the next figure here. So I've put stills of it. On the top, you see the each intermediate stage as we map a predictive receiver function onto the observed receiver function, and the misfit measure is the area between the 2, which is essentially how far these curves have moved. The point is that in the least squares case, all it knows about is the amplitude of the target at the same time where I am, and that's why it only moves the amplitude up and down. That's all it can do. It's in the definition of the least squares misfit function. And I take there are, of course, many other misfit functions, correlation, very, very many, but this is the most common. And I just want to compare it to that sort of straw man. What we would like to do is translate the waveform, because this really is a very similar waveform. It's just offset in time. But a least squares misfit function doesn't know that, and it's all it's trying to do is move the amplitudes up and down. And basically, many misfit functions use the time to compare where we should be looking at amplitudes. So this is fixes the time, uses that the independent variable, and looks at the amplitude. In a transport framework, which is the bottom, both time and amplitude change. And that's because we're transporting essentially the sand of the predicted waveform to the sand of the observed waveform. And what it does, you can see the, hopefully you can see the colored parts there. It smoothly maps one amplitude onto another. In fact, it decreases it and increases it. And that is the pathway of one implementation of optimal transport for this problem. And really the point of this is to show you that one is limited to changing amplitudes at fixed times, and the other one is not limited by that. It changes both amplitudes and times to smoothly map one waveform onto another. And in doing so, has a different, completely different path and a completely different measure of distance. And I would argue that the bottom is what you would do visually. You would like to map one onto the other. That's how you would transport it. A computer under a misfit function doesn't know that. It's simply saying, I have to match this amplitude at this time to this amplitude at this time, and I'll just try and look at the distance between them. Okay, so I hope I've given you an idea that optimal transport can do the same thing, as it's the same, fits into the same space as a misfit function here, and the Wasserstein distance is an alternate then to all measures of distance that regard time as fixed and look at amplitude. Okay, so this subject is not new to geophysics. In fact, the exploration geophysicists have been working on optimal transport for at least 8 years or so. And Bjorn Enquist and co-workers were the first into this from papers from about 2014 onwards. And Ludo Metivier, with some work from the Grenoble group, have also been working in the same area of full waveform inversion in exploration geophysics, and they have done a different style, worked on a different style, and you can see I've written words next to them. The Enquist group have forged on with what we call the Monge ampere solver to calculate optimal transport, which I'm not going to go into, which is for p equals 2. And the Metivier group have used a dual, what we call dual formulation of optimization, which has certain advantages if p equals 1. So 2 different ways of solving optimal transport and many variants around that in a whole series of papers. And this has caught the attention of the exploration community. It's broken out of that discipline in more recent times with 2 pieces of work here by, I'm going to pronounce his name wrong, Hejazian on seismic receiver functions and Huang on gravity inversion. So there are other people trying to apply this idea. And what I'm going to show you next is our take on the whole thing of trying to apply this Wasserstein distance to the inversion of waveforms of a sort of more global geophysics, crustal geophysics nature, where the problems are slightly different. But each of these areas, they differ in how they've calculated the Wasserstein, what value of P they've used, whether they do trace by trace or all at once. In full waveform inversion, you might have a whole image. So they've tried to use image methods. So there's quite a bit of difference. And really, how you best apply this to any one problem, I think, is an open issue. And it's certainly an evolving field. But there's a fair bit of work in geophysics in one direction, and I think it's time for this to explode across the spectrum. Now, okay, for the keen-eyed spotters there, most of you will realize I've talked about optimal transport being a problem of PDF to PDF, i.e. a positive probability distribution transforming into another. That's technically what it is. And waveforms aren't positive, yeah? They're wiggled, they're positive and negative, of course. And so all of these authors, including me, have had to transform a positive, a positive and negative time series into a positive signal. And how you do that is frankly a little bit arbitrary. People have tested multiple ideas. 2 are represented here. The top one simply adding a constant, which turns out to have lots of horrible properties to it. The second one is to take the absolute values, which is very common. So my blue signal here, I've got a Ricker wavelet, becomes positive on the right, and we map the positive signal to the positive observed and predicted. But there are many other ways of doing it. In the literature, people have tried to map positive to negative and negative to positive. They've also done what we call like with like, which is only mapping the positive to the positive part of the signal and the negative to the negative part of the signal. And you can do these. They each have, there's nothing really natural about any of them. They all have inadequacies. And really part of the game is how do you really properly pose a problem where we can try and avoid this positive and negative business and turn our object, which may be a time series, into a positive object. And a really innovative solution from Grenoble group was to consider it as a set of dot points. So you put a whole mass, a set of masses on your observed and predicted waveforms here. And rather than trying to map the curves, you try and map the points in 2D. Now they're just locations. Positive and negative don't actually mean anything. You're mapping points. And this is what they, the group call graph space OT. And they've implemented this, and it works better than earlier attempts at the same thing. Now I'm going to take an idea. So this one depends upon your distance metric. I'm going to take an idea which is in the line of this one here, but has a sort of different dimensionality to it. And we'll see, I think it's appropriate for more general problems. Now, here's our take on the idea. How do you turn a waveform or time series of anything into a nice probability positive function? After lots of scratching and experimenting, we've come up with this thought. 2 steps. First step is to take our waveform, which is our solid blue line here, and essentially find the distance function across our window. We're going to assume we have a time window, and in this case, an amplitude window. And any point on the plane, you can find the nearest point to the waveform. And I've contoured that here. The blue contours are on the positive side, the green contours on the negative side. So by making a distance function across the plane, I've now turned my waveform into a 2D function, which is small, zero along the waveform because the distance is naught. And as you move away, it gets larger and larger. Yeah? So the amplitude goes up away from the waveform and goes to zero on the waveform. And in some sense, that's the opposite of what we want. Yeah? We'd like to have a probability distribution where the maximum is meaningful and the minimum small parts are furthest away, are least interest. We don't want to have high amplitude far away from the waveform. We want high amplitude near the waveform. So what are we going to do? Very simply, we can just put the exponential to that distance function. And these are my probability distributions I'm making from a time series. I've introduced a fiddle factor called lambda here, which rescales the distance. If you look at the left-hand side, now my original waveform now is the crest, you can think of it as the crest of a mountain range. And the steepness of that mountain range is determined by the shape of the waveform and the distance metric, which is given by my simple scalar here, lambda. So for small lambda, I have a highly peaked function around my waveform, and for large lambda, it's like a standard deviation. It actually goes smaller. It more gently slopes away. So I give more weight further away. So lambda is an arbitrary choice, and it turns out that really it's almost set and forget in these problems because it doesn't seem to make much difference. But now I've got a positive function where I've encoded the waveform into the PDF, and that's a sort of interesting object. And I'm going to try and do optimal transport by comparing observed PDFs here to predicted. Okay, so the keen-eyed spotter review will say, I thought you said it was only cheap in 1D, not in 2D. That's true. So now I'm going to introduce an approximation. I'm going to say I'd much rather use my 1D solution than trying to do a 2D solution. The idea is to compare two 2D PDFs, which I think at the moment is a bit expensive. So I'm going to take a shortcut and say, well, what I'll do is on the left-hand side here, I will take my 2D PDF and take a marginal over time, which gives me my blue function at the bottom, and a marginal over amplitude, which gives me my blue function on the left-hand side here. And now I have two 1D PDFs. I have lost information in doing this, but I've coded most of that structure back into two 1D PDFs. Both PDFs here contain information on amplitude and time. It's not just that what we might call the time marginal contains only time information, it contains amplitude information, and same is true for the other one. Now I'll compare my two sets of 1D PDFs between observed and synthetic, and that's how I'll go to do my Wasserstein distance, and we'll call this the marginal Wasserstein in 2D, comparing two sets of 1D PDFs. And because the benefits gained from that, analytical derivatives, fast, exact solutions to the 1D problem far outweigh what we might lose in throwing away the 2D. At least that's my observation. So in this approach then, we take advantage of the 1D analytical solution. We'll handle time windows about predicted and observed. So the time windows can be arbitrary. That's the point. When we're far away from a solution, the waveforms don't match. That's when the nonlinearity comes in. And essentially, the two waveforms do not have to have the same time window. They can be any time windows, non-overlapping time windows. Equally, they can have different amplitude windows. And we can calculate derivatives of this problem analytically. We can propagate through even into the marginal. So we're making a compromise here to try and get things tight, exact, and fast. Now, putting it all together, this is the approach we're proposing and we're going to experiment with. On the right-hand side are our Earth model parameters, whatever they may be. In this case, they calculate seismic waveforms. It could be other things, but it's a time series. And that time series then produces what I'm calling a fingerprint, which I showed you is my distance function. That's the orange box in the middle. From the orange box, I simply make a probability distribution, which is the blue box. And then I can do optimal transport between my marginal Wassersteins in the blue box. Now, this all sounds like a bit of a bother, a bit of a palaver. It turns out that every part of this is analytical except the first part, which is whatever the forward problem is. So if one has analytical derivatives, let's say, that moves the Earth model into the seismic, I can actually propagate all the way through and get analytical derivatives out. If you have an adjoint solver or any other, typically in an optimization framework, the derivatives on the right-hand side would have to come in from the Earth model. So that depends on the Earth model. Really, I've said seismic waveform, you could think of that as time series, and this formalism would work, and we'll end up with a nice scalar misfit function for any choice of P we might make. So I hope that's clear. We're putting the Lego bits together, and it has some choices have been made, and it has some compromises. Now, I'm going to go through two examples here. The first is just using very simple, trying to fit so there's no Earth model in this one. I'm just fitting a double wicker. This is inspired by the work of Enquist, who showed examples like this for a single wicker. So I've just made it a little bit more complicated. And again, I had some lovely animations that you'll want to look at later, but you probably won't see. The predicted waveform has to match the observed waveform. So I have three unknowns. I'm going to directly manipulate the waveform rather than having an Earth model. My three unknowns are going to be time shift. So the blue can move backwards and forwards, left and right. An amplitude shift, as shown by the second column, it can go up and down, and it can change its frequency. Because this is a simple analytical waveform, it's a double Ricker wavelet, I can control these directly, I can calculate derivatives, they're trivial, so I don't have any Earth model or anything complicated, it's just simply showing how we fit data. Now, in the next one, if we can get the thing going, now, oh, it's working for me, hopefully it's working for you. Here's just simply scanning the predicted waveform over the Ricker wavelet. And the middle one shows the L2 misfit, because as we go again, as one moves over the other, the L2 misfit, of course, has multiple minima as we line up. And the Wasserstein distance, calculated in the way I've just described, is perfectly quadratic for this problem. So this has been demonstrated previously by Enquist for a different formulation, and we're checking that it works for ours, and we're very happy. The multimodal misfit function in the middle has become a single quadratic in the bottom. Okay, so making that more complicated into the 3-parameter problem I looked at, this is the equivalent of the L2 misfit surface as a function of 2 parameters, the time shift amplitude and the amplitude shift. There's also a frequency change. But if we do that, we see this folded surface here in the synthetic line, the synthetic problem, the red dashed line, as you can see, it's in the valley in the middle is where the global minimum is. And optimization problems in this sort of surface can easily get trapped in local minima. This is still a trivially toy problem, but you can see how the local derivative-based optimization can get trapped. Now, here are the two surfaces for the optimal transport for the same problem, where P equals 2 on the top right and P equals 1, the top left. So ones, and below, I've actually projected the contours of this onto the surface below. Hopefully you can see those. In the P equals 2 case, they're perfectly quadratic. In this case, the semi-major axis along the amplitude is much longer than it is across, but it's still quadratic. And in the other one, it's exactly as you get in an L1 norm. It's a diamond shape. So starting from almost anywhere, we would see on the top right, we would converge to the global minimum. Whereas in the L2, it depends, we have to be very close to converge, i.e. we have to have our phases lined up. Now, I did actually have an animation of that working. I'll skip over this. This is simply saying that we can use analytical derivatives to work throughout, and they're exact, is what I mentioned before. We use the chain rule. It's the same process. And let's see if my animations work. Now, the animation is going to show in the middle here, the blue as it moves towards the orange, as we'll see what the character of the fit to the data is as I invert for my 3 parameters. I do a simple optimization. The top right figure will show you the Wasserstein distance as it's changing as the waveform moves, and the bottom one will show the least squares waveform misfit for the same path. We're optimizing the Wasserstein here, but we're just monitoring what the least squares fit would look like if we calculated it at the same position. The least squares is not affecting the path here. It's not affecting the inversion. We're using the Wasserstein. We're just using that as a monitoring. Now, can we get it to work? Oh, bugger. It doesn't work. Never mind. What you would see is the blue curve. I'll try it again just to be optimistic. Nope. I'm seeing the bar go across the bottom. Unfortunately, you're not seeing it work. What you would see is that, first of all, the blue waveform moves in time. I'm not telling it to do that. That's just where the biggest gradient is. It lines up with the orange curve. It then adjusts its frequency and amplitude together and fits it as well as possible within the noise. And what you'll see in the top right is the Wasserstein distance smoothly goes down and down and down. It turns out that the least squares misfit will actually jumps over a valley. So you would see that go down and go up and then go down again. And that's simply showing that although we're not using the least squares misfit here, it's jumping over the valleys that you would have, or the hills, into the global well of global minimum. So unfortunately, it's a bugger. Never mind. You can have a look later. Now, generalizing that with my final example before I finish here is more recent work on doing this to waveforms for a regional case in the context of seismic source location and moment tensor inversion. Now, I've given simple examples. Now we have an Earth model. We have a seismic source. We have full seismic waveforms being calculated. In fact, they're being calculated in a 1D Earth model here, and they're actually displacement waveforms. They're using the approach of O'Toole and Woodhouse 2011, O'Toole, Valentine and Woodhouse 2012. So these are essentially high rate GPS displacement waveforms. They're not, if you differentiate them, you'd get effectively seismograms, but here we have an extra complexity and that we're trying to fit the displacement waveforms. So I'm going to have an alternating source and moment tensor inversion. We're going to use gradient based. I'm going to compare least squares to Wasserstein and see how well one converges in a bigger problem like this. And we have a 1D Earth model. So it's a more serious, larger problem. I actually have 11 seismic stations and 3 component data. So I actually have 3 times 11, 33 different sets of observed and predicted waveforms that I'm trying to fit simultaneously here. Now the dashed line is the starting waveform predicted from my starting model, one starting guess that turns out to be 56 kilometers away, which is a considerable distance in this context. It's considerable because you can see that the observed waveform, or it's synthetic with noise here, the solid, doesn't line up. The peaks don't line up with the initial predictions. And that is the case. You're outside the local linear regime and you're going to have trouble with optimization with the least squares norm. But so we're starting far enough away for nonlinearity to be a serious problem here. Now, to do this, I've used my waveforms. The only generalization what I've said before is that I've used 2 different time windows and I've rescaled my amplitudes using this mapping here so that we can map, because our full waveform inversion here doesn't know, we can't control where the amplitudes would be. We want the amplitudes to be within our window. Predicted amplitudes will change as we change our source or as we change Earth model parameters. And to make sure we always capture it, I've mapped plus or minus infinity in amplitude to a finite amplitude using the transformation you see. So I've transformed it to give me a nice finite box. And if you do that, again, you can use analytical derivatives through that process. We can compare our fingerprint to our observed and our calculated, and away we go. We try and minimize the Wasserstein. Okay, so before I show some minimization, I'll actually just do some cross sections to give you an idea of the Misfit function for this problem through 3 different depth layers. Now, this is the least squares Misfit function. The black dot is the true location, and because it's noisy, the minimum of the Misfit function, which is white here, is not quite at the black dot. That's just due to noise in the waveform, correlated noise. And you can see in the bottom slices here at a lower depth, it's almost sort of nicely global. The least squares Misfit from a deep solution works reasonably well here. This is only a cut through a three-dimensional space. Yeah, so we're just seeing the cut, but it's well behaved. But in shallow cases, i.e. the top two at 10 and 20 kilometers depth, you see multiple minima, and particularly in the top left-hand side, you see significant local minima. And this is where phases are not being lined up in the least squares, and so least squares respond to that by having multiple minima in the problem, and we can get trapped in those if we try and locate this problem by fitting these waveforms. We can easily get trapped, and we will get trapped. We'll show. On the right, so the left-hand side figure here is the same figure, and the right-hand side of the corresponding Misfit function for the Wasserstein distance. So you can see that it's, in some sense, better behaved. It's equally nice in the deeper parts of the lower panels, but as you go to higher, there's some suggestion it's not local minima free, but there's some suggestion that it's more dominated by the global minima. It looks, so it's just a descriptive arm wavy qualitative, it looks better behaved, but is it better behaved? So let's try and test it out. And to test it out, I'm actually going to perform multiple source locations on the left-hand side and on the right-hand side, using the initial waveforms that we fit here. I'm just showing you some results to show you that we do actually fit the waveforms. Here, the initial waveforms, I've only chosen two stations. At the top are the same as you've seen before. The bottom here are the best fit solutions from that starting guess according to the L2 and the Wasserstein. Now, the L2 is the black dashed line, and you can see in all the panels that mostly the L2 doesn't fit the data because it's converged to a local minima for this problem, whereas the Wasserstein does fit the data because it's got into the final solution, the good solution. The Wasserstein solution in this particular case is about 1 kilometer from the truth, which means it's within the uncertainty, and the L2 converges to 32 kilometers from the truth. It's hit a local minima. Now, of course, these results will be dependent upon whatever optimization method I use, and they could be improved by doing something better, but I've used exactly the same optimization method for the two, starting from exactly the same position. Now, that's just one case to show you fit to data, that this is a case where Wasserstein works and L2 doesn't, but let's compare it across a whole range of starting solutions. So if you look at the left-hand side here, and we're almost at my final slide, the cyan dots are different XY locations that I've started. I've done 48 repeat inversions here, trying to find the solution from the locations of the blue dots at 4 different depths. So we're up to 60 kilometers away, which is significant distance in this for this problem, in our blue dots. And so it's 12 times 4, 48, yes, 48 different inversions. And I've done that for both the L2 norm and the Wasserstein as I've described it. And on the right-hand side is the summary, hero figure of the results that capitalizes all of these, is that I plotted the error in the OT solution and the error in the L2 solution. Now, this is a log-log graph. The dashed lines show 1 kilometer error from the true solution. That previous example was about 1 kilometer out. And you can say if we're below the green dot there, we've converged with 1 kilometer in the L2. And if we're to the left of the green dot, of the green dashed line, we've converged to less than 1 kilometer from the OT solution. So I'm plotting essentially the errors of exactly the same starting point, OT versus L2. And you can see that a large number of the solutions are to the left of the green line, but outside the L2 solution. So they have, some are in both, some have converged, both have converged, and they're essentially the ones closest in. As you go further away, I think there's a reasonable argument here that the OT solution has been more, has lent itself more to convergence and therefore countered the nonlinearity to some extent. In the Ricker problem, it was perfect, it will converge from everywhere. It's not true here. We still have solutions that don't converge, in this case for the Wasserstein and the L2, so they're in the top right. So, but overall, there's 29% of convergence from the least squares and 79% from the Wasserstein. So I think that's quantitative evidence that the process has been improved. We can converge from further out, and it's an alternative Misfit function for this problem. So jumping onto my conclusions, we've got there in the end. So this is, we've formed a new approach to optimal transport that is sort of generalized for time signals in different windows with any amplitude variation. we've exploited analytical solutions and derivatives to facilitate this. Without doing this, I think, would it really be worth it? It'd be so expensive, we wouldn't really probably gain much. But it is analytical, so it's all hunky-dory. We can use it in a convenient framework. I think there's quantitative evidence that improves, essentially widens the basin of attraction. So non-linear problems become easier to attack with optimization. And I've really just taken an off-the-shelf optimization method here. So this could be used for the starting point for then uncertainty analysis. We'd still do that in the normal way. Once we're in the global minimum, we're happy, we can use linearized uncertainty analysis, and that's what I suggest we do here. So these directions are building on the work from the full waveform inversion, but there are many open issues of how I've used the Wasserstein distance here, but how we might utilize the transport plans and maps in geophysics, and how we might attack that bigger problem of Bayesian inference, which I think is certainly not low-hanging fruit, but I think a very interesting way to look at generalized solutions to problems from a Bayesian perspective in the optimization framework. I'm not suggesting that's practical yet. I'm simply saying that there is an alternative way of defining all problems in that context, and it's sort of interesting to explore. Okay, thank you. I'll leave it there. I'm sorry I've gone over time.
Well, thank you very much, Malcolm. That was absolutely wonderful. It really, you know, I think it's going to revolutionize the way we look at inverse problems. I love the fact that you don't get stuck in local minima, and that's a huge issue for us in EM studies because it's a highly nonlinear problem, and so avoiding those are wonderful for us. And I hope I see a lot of EM people are listening. I hope this gets taken up. If you would like to put your questions to Malcolm in the Q&A box, and if you want to speak to him, just raise your hand and I'll make you I'll unmute you so you can speak. But we have a question already that came in early, actually, from Yago Ali regarding the cow-torus transform. Does that mean optimal transport can handle varying topology?
So the answer to that is yes, absolutely. If you think of it in 1D, it can handle any positive function that can be effectively its probability distributions. It can be multimodal in 2D, as ugly as you like, but it's single valued. Solomon worked out how to represent. So there is there's some stuff under the hood in this example of how to represent a shape in that context. So there is a parameterization inherent in this example, but with some parameterization tricks in this case, you can represent topologically complex beasts, as you see here in optimal transport. I should add, the methodology is used here is essentially a version of a smooth optimal transport, using Solomon's work is essentially smoothing this to make it more stable and doing it in high dimensions and doing it particularly fast. And this is, his work is more in the computer science literature, and it's sort of taking off there. If anyone's ever trained a neural network, there's a paper that was, I think it got 1,500 sites in about 3 or 4 years called Wasserstein GAN. And that's essentially using the same type of measure here based on the same principles to compare images and train neural networks. So this sort of stuff has taken off in that field as a misfit function.
Yeah, thank you, Malcolm. I think a lot for almost everybody, this is such new material that we're struggling to think of sensible questions to ask you.
Of course.
Yeah, I'm not seeing any others coming. Okay, if there's no more questions from the audience, I'd like to again thank you, Malcolm, very much for appearing and presenting to this revolutionary way, for me, from my perspective, revolutionary way of solving the inverse problem, which seems to be far more direct and avoid a lot of the issues that we have.
Thank you. And I apologize for my movies not working properly, but that's life. Yeah.
Yeah.
Sorry.
This recording will be live well, tomorrow morning my time, and Malcolm is sending me the presentation, and that will be live too. So I'd just like to sign off by grabbing Malcolm's screen back from him and reminding people. Oh, where do we have?
I stopped sharing. Thank you, Kathy. I see a message from Kathy there. Nice to hear from you.
I think I've lost the. Well,
I've stopped sharing.
Yeah, I've lost what I was going to show. Just to remind everybody, next week is Andreas Junger at 1300 UT on anisotropy. So again, thank you, Malcolm, and
Thank you.
goodbye, everybody. Thanks for attending.